Hello there, and welcome to the Sleepless Scientist. Tonight, we're journeying back through deep time to explore one of Earth's most fascinating chapters, the story of Pangea, the supercontinent that once united all the land we know into a single vast landmass. We'll trace the slow dance of continents across hundreds of millions of years, from the fiery birth of our planet's crust to the breaking apart of this ancient world, and the drifting continents that followed. It's a story of unimaginable timescales, of forces hidden beneath our feet, of life adapting to a changing world. So settle in, let your mind drift across geological ages, and allow the patient movement of Earth itself to carry you gently toward rest. And just before we begin, if these calm, curious explorations help you unwind, or give you a quiet way to end your day, consider liking and subscribing to the channel. It helps others find their way here too. One sleepy soul at a time. The story of continents begins. Long before maps, before nations, before humans walked the earth, the continents themselves were wanderers. They've drifted across the surface of our planet for billions of years, colliding, merging, splitting apart in an endless patient dance. The story of Pangea is just one chapter in this vast geological epic. But it's a chapter that shaped the world we know today. Every mountain range, every ocean basin, every coastline carries echoes of this ancient supercontinent. To understand Pangea is to understand that the ground beneath our feet isn't as permanent as it seems. The continents are passengers on vast plates of rock, floating on a layer of partially molten material, driven by heat from Earth's core. They move slowly, just centimeters per year, but over millions of years, those tiny movements reshape the entire planet. Continents that are now separated by thousands of kilometers of ocean were once joined. Animals that seem impossibly distant cousins once lived side by side. The Earth is a dynamic planet, constantly reinventing itself, and Pangea represents a moment when all the scattered pieces came together into one. The young Earth in motion. Picture Earth 4.5 billion years ago, a molten sphere cooling in the darkness of space, bombarded by asteroids and comets. Its surface an ocean of liquid rock, glowing red and orange. There were no continents yet, no oceans, no atmosphere as we know it, just heat and violence, and the slow process of planetary formation. The young Earth was nothing like the world we inhabit. It spun faster. Days were only 5 or 6 hours long. The moon loomed enormous in the sky, orbiting much closer than it does today. Volcanic eruptions covered the surface, releasing gases that would eventually form the atmosphere. The temperature was unbearable, hot enough to vaporize water. Yet even in this inferno, the processes that would eventually create continents had already begun. Denser materials sank toward the core, while lighter materials rose to the surface. The planet was sorting itself by density, creating the layered structure of core, mantle, and crust. It would take hundreds of millions of years for the surface to cool enough for solid rock to form, and longer still for the first proto-continents to emerge. But the stage was being set for everything that would follow. A planet of fire and stone. As Earth cooled, a thin crust formed on the surface. Fragile at first, constantly broken and reformed by volcanic activity and impacts. This wasn't yet the stable crust we know today. It was thin, hot, easily melted, but it was a beginning. Beneath this crust, convection currents churned through the mantle, hot material rising from deep within, cooling near the surface, sinking again in a slow, endless cycle. These currents created stresses in the crust, fracturing it, moving the pieces around. Even before plate tectonics, as we understand it today, the surface was in motion. Volcanoes erupted constantly, building new rock, releasing gases that accumulated in the atmosphere. Water vapor, carbon dioxide, nitrogen, trace amounts of other gases. These formed the primordial atmosphere, hostile to life as we know it, but essential to what would come. Eventually, perhaps around 4 billion years ago, the surface cooled enough for water to condense. Rain fell for the first time, torrential storms that may have lasted for millions of years, filling the low places and creating the first oceans. The planet was transforming from a world of fire to one of water and stone. The cooling of the crust. The cooling of Earth's crust was gradual, uneven, punctuated by catastrophes. Large impacts reheated the surface, melting rock and reversing progress. But between these violent events, the crust thickened and stabilized. Different types of rock began forming through various processes. Basalt formed from rapidly cooled lava, dark and dense, similar to the oceanic crust we have today. Granite formed through more complex processes, lighter in color and density, buoyant compared to basalt. These lighter rocks couldn't sink back into the mantle as easily. They accumulated, forming the seeds of the first continents. The early crust was probably thinner than today's, more easily recycled, with proto-continents that formed and were destroyed repeatedly. Only the most stable accumulations persisted. The oldest rocks found on Earth today date back about 4 billion years, fragments of ancient crust that somehow survived the violent early eons. They're rare, precious, windows into an alien Earth. Most of the early crust has been recycled, melted, and reformed countless times. The crust we walk on today is the product of billions of years of processing and reprocessing, refined and sorted by geological forces. The first oceans form. When the surface temperature dropped below the boiling point of water, something remarkable happened. The water vapor in the atmosphere began to condense. Rain fell, not gentle showers but violent storms, and it fell for an immensely long time. The water accumulated in low-lying areas, pooling, deepening, eventually covering much of the planet's surface. The first ocean was born, though it would have been very different from modern oceans. It was probably more acidic, containing dissolved minerals leached from rocks. It was likely warmer, heated from below by the still hot crust, and it contained no life, at least not at first. But water changes everything. It weathers rock, breaking it down chemically and physically. It transports sediments, depositing them in layers. It allows certain chemical reactions that can't occur in its absence. The presence of liquid water on Earth's surface created new possibilities, new pathways for change. Gradually, through processes we're still working to understand, life emerged in these early oceans. Simple at first, single-celled organisms, but capable of evolution, of increasing complexity. The oceans became nurseries for life, and life in turn would begin reshaping the planet. The birth of the early continents. The first continents were nothing like the land masses we know today. They were small, scattered patches of lighter rock, rising above the ocean's surface, or floating just beneath it. Think of them as islands, archipelagos, constantly forming and eroding and reforming. But gradually, over hundreds of millions of years, these fragments accumulated. The process involved volcanism, the melting and remelting of rock, the buoyant rise of lighter minerals, and the patient accumulation of sediments. Some of the oldest continental crust, called cratons, formed between 3.5 and 2.5 billion years ago. These ancient cores still exist, buried at the hearts of modern continents. Bits of Canada, Australia, Africa, and Siberia contain rock from this incomprehensibly ancient time. These cratons are remarkably stable. Once formed, they resist being dragged back into the mantle, instead floating on the denser basalt like corks on water. Over time, they merged, broke apart, and merged again in different configurations. Each collision added material to their edges. Each rifting left fragments behind. The continents grew through a complex history of assembly and dispersal, a story written in the rocks for those who learn to read it. The dance of the tectonic plates. Beneath the surface, the Earth is in constant motion. The mantle, though solid rock, flows over geological timescales like an extremely thick fluid, Heat from the core warms the deepest mantle, causing it to expand and rise. As it rises, it cools, eventually sinking again in a continuous cycle of convection. This churning drives everything that happens at the surface. The crust is broken into pieces, tectonic plates, that ride on top of the flowing mantle. These plates move in response to the currents beneath them, grinding against each other, pulling apart, colliding. At divergent boundaries, plates separate and new crust forms from upwelling magma. At convergent boundaries, plates collide. One may dive beneath the other in subduction, melting as it descends, or they may crumple together, building mountains. At transform boundaries, plates slide past each other horizontally, accumulating stress that releases in earthquakes. This system, plate tectonics, is unique to Earth among the planets we've studied. It's driven by our planet's internal heat, the residual warmth from formation, plus heat generated by radioactive decay. The dance of the plates has continued for billions of years and will continue for billions more until the Earth's interior cools enough that convection slows and finally stops. The hidden forces beneath our feet. We live on the surface, seeing only the results of deeper processes. Mountains rise, earthquakes shake, volcanoes erupt. These are symptoms of the forces operating far below. The mantle churns slowly, moving just centimeters per year, but with unstoppable force. Pressure and temperature increase with depth. Rock that's solid near the surface becomes ductile deeper down, able to flow when subjected to the immense pressures of the deep earth. The core, iron and nickel, is even hotter, temperatures comparable to the surface of the sun. The outer core is liquid, its motion generating Earth's magnetic field. The inner core, despite the heat, is solid, compressed by the weight of the entire planet above it into crystalline metal. All of this exists beneath us, a layered world within a world, driving the geology we observe. The heat flowing from the interior is the engine that powers plate tectonics. Where hot plumes rise, continents may dome and crack. Where cold slabs sink, ocean trenches form, and volcanoes erupt. Everything is connected, surface to core, in a system that has operated for billions of years. Understanding these hidden forces helps us understand why the continents drift, why Pangea formed, and why it eventually broke apart. The slow drift of landmasses, continents, move at about the speed your fingernails grow, a few centimeters per year at most. It seems impossibly slow, yet over millions of years, it transforms the planet. In a human lifetime, you'd never notice. In 1,000 years, the change would still be imperceptible. But over 1,000,000 years, continents shift hundreds of kilometers. Over 100 million years, they cross entire oceans. This slow drift has been happening since the first continents formed. They've wandered across the globe, sometimes isolated, sometimes colliding and merging. The configuration of continents affects everything: climate, patterns, ocean currents, the evolution and distribution of life. When continents cluster near the poles, ice ages become more likely. When they're scattered across the equator, climates tend to be warmer and more uniform. The positions of continents determine where mountains form, where deserts develop, where life flourishes or struggles. Understanding this drift requires thinking in timescales that dwarf human experience. We must imagine the planet as a dynamic system, constantly changing, never static. The world map we know is just one frame in a very long movie. Before our current configuration, there was Pangea. Before Pangea, other arrangements. And in the future, the continents will assemble into new patterns we can only predict. The idea of a moving Earth. For most of human history, people assumed the Earth was static and unchanging, its features permanent since creation. Mountains, oceans, continents. These seemed eternal fixtures. But careful observers notice puzzles. Why do the coastlines of South America and Africa look like they might fit together? Why are identical fossils found on continents, now separated by vast oceans? Why do ancient rocks in Scotland match rocks in North America? These questions suggested something remarkable, that the continents might not have always been where they are now. But the idea seemed absurd. How could entire continents move? What force could push them across the earth? Without a mechanism, the idea remained speculation, dismissed by most scientists. The breakthrough came in the early 20th century, though it took decades for the scientific community to accept it. The story of this discovery is as fascinating as the discovery itself, a tale of ignored evidence, ridiculed theories, and eventual vindication. It shows how science works, how ideas that seem revolutionary and impossible can become established fact once enough evidence accumulates. The theory of continental drift transformed geology, turning it from a descriptive science into one that could explain how the Earth works, how it changes, and why it looks the way it does today. The theory that changed geology. The theory of continental drift proposed that continents were once joined and have since moved apart. It explained the distribution of fossils, the matching rock formations on distant continents, and the fit of coastlines. But when first proposed, it was met with skepticism and even mockery. The main objection was reasonable. What force could move continents? The proposer suggested various mechanisms, but none were convincing. For decades, the theory languished, accepted by some, but rejected by the geological establishment. The vindication came from an unexpected source: the ocean floor. In the mid-20th century, new technologies allowed scientists to map the seafloor in detail for the first time. What they found was astonishing: mid-ocean ridges, underwater mountain ranges running through the center of ocean basins, patterns of magnetic stripes in the seafloor rocks, symmetrical on either side of these ridges, deep trenches where oceanic crust was being dragged down and destroyed. The ocean floor wasn't old and static. It was young, actively forming at ridges and being recycled at trenches. This provided the mechanism that had been missing. The seafloor was spreading, pushing continents apart. The theory of plate tectonics was born, incorporating continental drift as part of a larger system. Geology would never be the same. Alfred Wegener and the puzzle of continents. Alfred Wegener was a German meteorologist and geophysicist, not a geologist by training. Perhaps this outsider status allowed him to see what specialists missed. In the early 1900s, he noticed the remarkable fit between the coastlines of South America and Africa. Others had noticed this before, but Wegener pursued the idea systematically. He gathered evidence from multiple fields: geology, paleontology, climatology. He showed that rock formations in South America matched those in Africa, not just in type, but in age and sequence. He documented identical fossils on continents, now separated by oceans, fossils of organisms that couldn't possibly have crossed such barriers. He noted evidence of ancient glaciers in places now tropical, suggesting continents had moved through different climate zones. In 1912, he proposed the theory of continental drift, suggesting all continents had once been united in a supercontinent he called Pangea, Greek for all Earth. He published his ideas, expecting acceptance. Instead, he faced ridicule. Without a convincing mechanism, other scientists dismissed the theory as impossible. Wegener died in 1930 during an expedition to Greenland, his theory still largely rejected. He never lived to see his vindication. It wasn't until the 1960s, decades after his death, that plate tectonics provided the mechanism and confirmed his vision. Today, Wegener is recognized as a visionary who was right for partly wrong reasons, but right nonetheless. The clues found in ancient rocks. Rocks are storytellers. If you know their language, they record the conditions under which they formed: temperature, pressure, environment. By studying ancient rocks, geologists can reconstruct vanished worlds. One of the strongest evidences for Pangea comes from matching rock formations on different continents. Mountain ranges in the Appalachians of North America align with mountains in Scotland and Scandinavia, not just roughly but precisely. The same rock types, the same ages, the same sequence of formation. If you could push the continents back together, these mountain ranges would reconnect into a single ancient mountain chain. Similarly, distinctive rock formations in South America match those in Africa, as if a single formation was torn in half. These aren't coincidences or similar conditions producing similar rocks. The matches are too precise, too detailed. They indicate these rocks were once part of the same geological structure, later separated by continental drift. Ancient minerals also preserve magnetic information, showing which direction was north when the rocks formed. By studying these paleomagnetic signatures, scientists can determine where continents were located in the past. The evidence is overwhelming. Rocks from different continents tell chapters of the same story, a story of a time when all land was one. Fossils that cross the seas. Perhaps the most compelling evidence for Pangea comes from fossils. Certain species are found on multiple continents, now separated by vast oceans. Mesosaurus, a freshwater reptile from the Permian period, appears in both South America and Africa. This creature couldn't have swum across the Atlantic Ocean. Glossopteris, a distinctive seed fern, is found in South America, Africa, India, Antarctica, and Australia, all the continents that formed the southern part of Pangea. Identical earthworm fossils appear in Africa and South America. The same species of land snail occurs on opposite sides of the Atlantic. These distributions are impossible to explain if the continents have always been separate. There's no way these organisms could have crossed thousands of kilometers of ocean. But if the continents were once joined, the distributions make perfect sense. The organisms lived in a continuous habitat spanning the supercontinent. When Pangea broke apart, populations were isolated on separating fragments. The fossils that seem mysteriously distributed today are actually evidence of ancient unity. They're like torn pieces of a photograph, scattered now, but clearly part of the same original image. The fossils don't just support the theory of continental drift, they map out how the continents were connected, helping us reconstruct Pangea's shape. The evidence in the mountain ranges. Mountains tell the story of continental collisions. When two continents drift together and collide, neither can sink into the mantle. Both are too buoyant. Instead, they crumple, folding and thrusting upward, building mountains. The process is slow but irresistible. The Himalayas are rising today as India continues pushing into Asia, a collision that began around 50 million years ago. The mountains are still growing, lifted higher each year by the ongoing compression. Ancient mountain ranges reveal past collisions. The Appalachians in eastern North America were formed when North America collided with Africa during the assembly of Pangea, around 300 million years ago. They were once as tall as the Himalayas are today, perhaps taller. Erosion has worn them down to gentle peaks, but their structure still records that ancient collision. In Scotland, the Caledonian Mountains were formed by even earlier continental collisions. In Scandinavia, ancient mountains tell similar stories. These ranges, now separated by the Atlantic Ocean, were once part of a single enormous mountain chain that ran through the heart of Pangea. The mountains are scars, permanent records of the violent meetings of continents, preserved in folded and fractured rock for geologists to read hundreds of millions of years later. The matching coastlines of distant lands. Look at a map. Notice how the eastern coast of South America and the western coast of Africa seem like they could fit together, like puzzle pieces. This observation has intrigued people for centuries, at least since accurate world maps became available. But it's not just a rough similarity. When you account for the continental shelves, the shallow underwater extensions of the continents, the fit is remarkably precise. Computer models have tested this, moving the continents back together, and the match is nearly perfect. The bulge of Brazil nestles into the curve of West Africa. Features line up along the entire length of the connection. This can't be coincidence. The simplest explanation is that these coastlines were once joined and were torn apart when Pangea rifted. The same is true for other continental margins. The eastern coast of North America fits against northwestern Africa and southwestern Europe. Antarctica, Australia, India, and Madagascar fit together into the southern portion of Pangea. When you reassemble all these pieces, they lock together beautifully, recreating the supercontinent. The matching coastlines were one of the first clues that led to the theory of continental drift. They're visible to anyone with a map, suggesting something profound, that the familiar geography of our world is temporary, just one configuration in an endless series of rearrangements. The vision of a supercontinent. Imagine standing on Pangea. All around you, in every direction, stretches land. There are no oceans to cross, because all the oceans are on the other side of the world, merged into one vast ocean called Panthalassa, the All-Sea. You're standing on the only land, and it encompasses everything. Every environment exists on this single continent: mountains, deserts, forests, swamps, coastlines. But the interior, thousands of kilometers from any sea, is unlike anywhere on Earth today. It's dry, hot, subject to extremes. Coastal regions enjoy moderated climates, moisture from the ocean, seasonal patterns, but the deep interior suffers. Pangea wasn't evenly populated with life. Its center was largely barren, hostile, a vast desert larger than any that exists today. Life clung to the edges, where water was available, where climates were tolerable. This was the world for tens of millions of years during the late Paleozoic and early Mesozoic eras. It was the world that saw the worst extinction event in Earth's history. It was the world where reptiles rose to dominance, where the first dinosaurs appeared. Understanding Pangea helps us understand the evolution of life, the distribution of species, and the patterns we see in the fossil record. The birth of Pangea begins. Pangea didn't form suddenly. It was the result of a long, slow process of continental collisions spanning hundreds of millions of years. The story begins in the Precambrian, over 1 billion years ago, when earlier supercontinents existed and broke apart. By the early Paleozoic, several major landmasses drifted separately. Laurentia, which would become North America, Baltica, Northern Europe, Siberia, and the large southern continent, Gondwana, which included South America, Africa, India, Australia, and Antarctica. These continents had their own histories, their own assemblies from even earlier fragments. Through the Paleozoic era, these landmasses drifted closer. Around 450 million years ago, Laurentia and Baltica collided, forming a landmass called Laurussia. Around 350 million years ago, Laurussia collided with Gondwana, creating a massive mountain range. The Appalachians and their extensions, Siberia, joined around 300 million years ago, adding the final major piece. By the end of the Permian period, around 250 million years ago, Pangea was fully assembled. It stretched from pole to pole, a single continuous landmass surrounded by Panthalassa. This configuration would last for roughly 60 to 70 million years before the breakup began. But in geological terms, it was just a moment, one more arrangement in the endless cycling of continents. The colliding of ancient landmasses. When continents collide, the event unfolds over millions of years. But the forces involved are staggering. The edges of continents crumple. Sediments that accumulated on the continental margins are compressed and thrust upward. Rock layers fold into impossible curves, pressed by forces that can't be resisted. Faults form where rock breaks under stress. Great slabs thrust over each other. Volcanic activity often accompanies these collisions as rock is forced down and melted. The collision that formed Pangea wasn't a single event, but a series of impacts as various landmasses came together. Each collision built mountains, deformed crust, and welded continents together. The scars of these ancient collisions remain today, visible in the structure of mountain ranges and the patterns of rock formations. In some places, you can walk across the boundary where two ancient continents joined, stepping from rock that formed on one continent to rock that formed on another, now permanently fused. The collision zones became the interior of Pangea, regions far from any coast, elevated and transformed by the violence of the meetings. These were the suture zones, geological scars marking where separate worlds became one. The formation of a single giant land, at its maximum extent, Pangea, covered about a third of Earth's surface. It was huge, but not as large as you might think. The modern continents combined cover about the same area, just spread out. What made Pangea remarkable was its configuration, a single continuous landmass that an animal could theoretically walk across from one end to the other. This had profound effects on climate, ocean currents, and the evolution of life. With all land in one place, ocean circulation was dramatically different from today. The Pangea Ocean flowed freely around the globe without continents in the way, creating powerful currents. The Tethys Sea, an embayment that indented Pangea's eastern coast, was the only significant gap in the landmass. Pangea's enormous size meant its interior was isolated from oceanic influences. Modern continents are narrow enough that moisture from oceans penetrates inland, but Pangea's interior was so vast that by the time air masses reached the center, they'd lost all their moisture. Rain fell on the coasts, but rarely inland. This created the largest desert in Earth's history, a super hot, super dry wasteland in Pangea's heart. The climate extremes of Pangea shaped evolution, creating pressures and opportunities that led to new forms of life adapted to harsh conditions. The world before the dinosaurs. When Pangea formed, dinosaurs didn't exist yet. The dominant land animals were synapsids, mammal-like reptiles that would eventually give rise to true mammals. These creatures came in remarkable variety. Some were small and scurrying. Others were massive predators with enormous skulls and saber-like teeth. Herbivores ranged from pig-sized to rhinoceros-sized, grazing on the primitive plants that covered the wetter regions. This was the Permian period, the last period of the Paleozoic era, a time of transition. The great coal forests of the Carboniferous period were gone, replaced by drier landscapes dominated by seed plants and conifers. Insects were diverse. Dragonflies with massive wingspans, early beetles, the ancestors of many modern groups. In the oceans, life flourished in warm, shallow seas around Pangea's edges. Coral reefs thrived. Trilobites, ancient arthropods that had persisted for hundreds of millions of years, were still present though declining. Marine reptiles were beginning to evolve, entering the seas from land. It was a world that would seem alien to us, but it was a fully developed biosphere, ecosystems, as complex and balanced as any that exist today. Then catastrophe struck, and nearly everything died. The end of the Paleozoic era. The Permian period ended with the worst extinction event in Earth's history. Roughly 96% of marine species went extinct. 70% of terrestrial vertebrate species vanished. It was the closest life on Earth has ever come to complete annihilation. The extinction unfolded over perhaps 60,000 years, rapid in geological terms, but still a long catastrophe measured in human timescales. The causes are still being researched, but several factors converged. Massive volcanic eruptions in what is now Siberia released enormous quantities of lava and gases, covering an area the size of Europe in basalt over 1 million years, with the peak activity coinciding with the extinction. The gases released, carbon dioxide, sulfur dioxide, methane, changed the atmosphere and climate dramatically. Global temperatures soared, perhaps by 10 degrees Celsius or more. Ocean temperatures rose, reducing the amount of oxygen dissolved in water. The oceans became acidic and oxygen depleted, suffocating marine life. On land, The heat and aridity intensified, pushing many species beyond their tolerance limits. The extinction was global, affecting all environments. When it was over, the world was empty. Ecosystems collapsed. The survivors few and struggling. Recovery would take millions of years, but from this catastrophe would emerge new forms of life that would eventually include the dinosaurs. The great mountains of the supercontinent. The assembly of Pangea created mountains on a scale difficult to imagine. When continents collided during the formation of the supercontinent, vast mountain ranges were thrust upward. The Appalachians, which we see today as worn and gentle peaks, were born from the collision of North America and Africa. When they were young, they may have been as tall as the Himalayas, perhaps reaching heights of 8,000 meters or more. To the east, where Europe and Asia joined, other mountains rose. The Urals, which still mark the boundary between Europe and Asia, are remnants of this ancient mountain building. In the south, where the various pieces of Gondwana sutured together, more mountains formed. These ranges created barriers across the supercontinent, affecting climate by blocking air masses and creating rain shadows. Rivers draining these mountains carved deep valleys, transporting sediment that would eventually become the sandstones and shales we find today. The mountains were gradually eroded by wind, water, and ice. The material worn away was carried by rivers to low-lying basins and coastal regions, where it accumulated in thick deposits. These sediments preserved the fossils of life from that time, creating the fossil record we study today. The mountains of Pangea are mostly gone now, worn away or buried, but their shadows remain in the geological structures that underlie modern landscapes. The central desert of Pangea. At the heart of Pangea lay a desert unlike any that exists today. It was vast, perhaps 3,000 kilometers across, isolated from any ocean, baked by the sun, and swept by hot winds. Rain almost never fell here. Any moisture that air masses carried from the coasts was long since wrung out by the time they reached the interior. The land was bare rock and sand, dunes stretching to the horizon, temperatures soaring during the day and plummeting at night. Very little could survive in such conditions. The fossil record from these interior regions is sparse. Few organisms lived there, and even fewer were preserved. The desert left its mark in the geological record as vast deposits of sandstone, sometimes showing the cross-bedding patterns of ancient dunes. These rocks, formed from sand dunes, buried and compressed over millions of years, are found today in places like the southwestern United States, part of the Colorado Plateau. When you visit these regions and see the red sandstone formations, you're looking at the remains of Pangea's central desert, sand dunes, frozen in stone. The desert wasn't completely lifeless. During brief wet periods, life may have penetrated the edges. Along seasonal streams, plants and animals might have survived, but mostly it was empty, a dead zone at the heart of the supercontinent. The endless interiors without rain. The size of Pangea created a climate extreme. On modern continents, moisture from oceans penetrates inland, carried by weather systems. Even the driest deserts receive occasional rain, but Pangea's interior was so vast, and the continental effect so strong, that moisture rarely reached the center. Air masses, traveling inland, would warm as they descended from mountains, further reducing their ability to hold moisture. By the time they reached the deep interior, they were bone dry. The result was a region of permanent drought, year after year, millennium after millennium. The aridity was intensified by Pangea's position, straddling the equator. The climate zones were strongly defined. Tropical regions near the equator, temperate zones at mid-latitudes, polar regions at high latitudes. But the interior, regardless of latitude, was dominated by the continental effect. This created evolutionary pressure. Only organisms highly adapted to aridity could survive in or near the interior. Reptiles, with their scaly skin that reduced water loss and their ability to produce eggs that could survive dry conditions, had advantages over amphibians. The harsh interior of Pangea may have driven key evolutionary developments that allowed the later rise of dinosaurs and mammals. The heat and dryness of an ancient world, Pangea's climate was extreme in ways that go beyond just dryness. The sheer mass of the supercontinent created what's called a continental climate. Large temperature swings between seasons and between day and night. Coastal regions were moderated by the ocean, but the interior experienced blazing hot summers and cold winters. Without the moderating influence of nearby water, temperatures could fluctuate wildly. Some climate models suggest summer temperatures in the interior might have exceeded 50 degrees Celsius, hot enough to be lethal to most organisms. Winter temperatures, while not as extreme, could drop below freezing in higher latitude regions. The combination of heat and aridity made much of the interior virtually uninhabitable. This had a profound effect on biodiversity. Species richness was concentrated in coastal regions, where conditions were more tolerable. The interior acted as a barrier, preventing migration and gene flow between coastal populations, potentially promoting speciation as isolated populations diverged. The extreme climate of Pangea's interior is one reason the supercontinent period saw relatively lower biodiversity compared to times when continents were more dispersed and climates more moderate. Life survived, but it was pushed to the edges, clinging to the more hospitable coastal zones. The early life that adapted to the land, life on Pangea, had to be tough. The organisms that thrived were those adapted to harsh conditions. Plants developed strategies to conserve water, thick cuticles on leaves, deep root systems, the ability to go dormant during droughts. Conifers, which had evolved in earlier periods, were well suited to these conditions. They spread across regions that were too dry for earlier plant groups. Cycads and seed ferns also flourished, their seeds allowing them to reproduce without the constant moisture that earlier plants required. Animals adapted as well. Reptiles, with their water-conserving skin and eggs with protective shells, had advantages over amphibians, which needed water for reproduction. The synapsids, mammal-like reptiles, dominated the land during the Permian period of Pangea. They ranged from small insectivores to large herbivores and fearsome predators. Some developed features that suggested endothermy, warm-bloodedness, which would have helped them survive the temperature extremes. After the Permian extinction, when many synapsid lineages were wiped out, the survivors gave rise to two major groups, the therapsids, which would eventually lead to true mammals, and the archosaurs, which would give rise to dinosaurs, pterosaurs, and crocodiles. The harsh conditions of Pangea shaped the evolution of life in ways that still echo today. The first forests and swamps. Not all of Pangea was desert. The coastal regions, particularly in the wetter latitudes, supported lush forests and extensive swamps. These areas were refuges for life, places where moisture was adequate and conditions tolerable. The forests of Pangea were different from modern ones. There were no flowering plants yet. Those would evolve much later. Instead, forests were dominated by conifers, tree ferns, cycads, and seed ferns. These plants created closed canopies, in some areas, deep shade and humid air beneath. Swamps formed in low-lying coastal areas, where water accumulated and drained slowly. These wetlands were incredibly productive, supporting diverse communities of plants and animals. The plant matter that accumulated in these swamps, buried and compressed over millions of years, formed coal deposits that we mine today. Insects thrived in these environments. The forests buzzed with the activity of primitive beetles, early flies, and countless other invertebrates. Amphibians still survived in these wet habitats. Though they were declining in diversity, reptiles hunted in the undergrowth, and small, early mammal-like creatures scurried through the leaf litter, hunting insects or feeding on seeds. The forests and swamps of Pangea were lifelines. ribbons of green and life-threading through an otherwise harsh world. The amphibians of shallow waters. Amphibians had ruled the Carboniferous period, thriving in the vast swamps and coal forests of that earlier time. But by the time Pangea formed, their dominance was waning. They needed water for reproduction. Their eggs lacked protective shells and had to be laid in ponds or streams. Their skin, permeable and moist, required humid environments. As Pangea's climate became drier, amphibians retreated to the remaining wetlands. They still existed in remarkable variety during the Permian period. Some were small and salamander-like. Others grew enormous. Temnospondyls reached lengths of several meters, crocodile-like predators lurking in shallow waters. These large amphibians were ambush hunters, waiting motionless until prey came close enough to snap up in their powerful jaws. They fed on fish, other amphibians, and even small reptiles, but the amphibians were living on borrowed time. The increasingly arid climate reduced available habitat. The Permian extinction hit them particularly hard. Many lineages vanished. The survivors were the ancestors of modern amphibians, frogs, salamanders, and the strange limbless caecilians. These groups would persist, but they would never again dominate terrestrial ecosystems. The age of amphibians was ending. The age of reptiles was beginning, and Pangea's harsh conditions favored those with better adaptations for dry land. The reptiles that conquered the dry earth. Reptiles were perfectly positioned to exploit Pangea's conditions. Their scaly skin reduced water loss, allowing them to venture far from water sources. Their eggs, enclosed in protective shells with their own water supply, could be laid on dry land. This freed them from dependence on aquatic environments for reproduction. The reptiles diversified explosively during the Pangea era, filling ecological niches from tiny insectivores to massive herbivores to fearsome predators. The synapsids, technically not true reptiles, but closely related, were particularly successful during the Permian period. Dimetrodon, with its distinctive sail, was an apex predator. Moschops, a barrel-bodied herbivore, browsed on tough vegetation. These animals weren't dinosaurs. They lived before the dinosaurs existed, but they were the dominant land vertebrates of their time. After the Permian extinction, different reptile groups rose to prominence. The archosaurs appeared, a lineage that would eventually split into crocodilians on one branch, and dinosaurs and pterosaurs on another. Early archosaurs were diverse, some quadrupedal, some bipedal, ranging from small and swift to large and powerful. They experimented with different body plans, different lifestyles. Some returned to the water, becoming the first marine reptiles. Others took to the air, and one lineage, emerging in the Triassic period after Pangea began to break apart, would become the dinosaurs. The rise of insects and early plants. Insects had been on land for hundreds of millions of years before Pangea formed, and they continued thriving during the Supercontinent era. They're remarkably adaptable creatures, able to exploit nearly any environment. During the Permian and Triassic periods, insects diversified into many modern orders. Beetles appeared and quickly became diverse, evolving to feed on plants, fungi, and other insects. True flies emerged, their larvae occupying aquatic habitats and decaying matter. Primitive wasps hunted other insects or parasitized them. The relationship between insects and plants was evolving in complexity. Some insects pollinated early seed plants, though the elaborate flowers and specialized pollinators of later periods hadn't yet evolved. Other insects fed on plant tissues, leaves, stems, wood. Plants developed defenses, chemical compounds that made them toxic or unpalatable. Insects evolved counter-defenses, the ability to detoxify plant chemicals. This evolutionary arms race drove diversification on both sides. The fossil record shows leaf damage from insect feeding, mines and galls created by insect larvae, evidence of interactions similar to what we see today. Despite Pangea's harsh interior, wherever plants grew, insects followed. They were the hidden majority, small but incredibly numerous, recycling nutrients, pollinating plants, serving as food for larger animals. The shallow seas around the edges. While Pangea's interior was largely barren, life flourished in the shallow seas surrounding the supercontinent. These warm tropical waters hosted coral reefs, communities of brachiopods and mollusks, and countless other organisms. The reefs built structures of calcium carbonate, creating habitats for fish and invertebrates. Trilobites, which had existed for hundreds of millions of years, were still present, though declining toward their final extinction at the end of the Permian. In their place, new groups were diversifying. Ammonites, cephalopods with coiled shells, were abundant, swimming through the water and hunting smaller prey. Early sharks patrolled the reefs, though they looked different from modern sharks, some with strange shapes and unusual tooth arrangements. The shallow seas were nurseries for life, places where productivity was high and conditions relatively stable. Continental shelves, the shallow underwater extensions of continents, were extensive, providing vast areas of habitat. These regions would be catastrophically affected by the Permian extinction, which hit marine ecosystems even harder than terrestrial ones. The ocean chemistry changes that accompanied the extinction, warming, acidification, oxygen depletion, devastated the shallow sea communities. But those that survived would rebound, evolving into new forms during the recovery period. The coral reefs of ancient oceans. Reefs have existed for hundreds of millions of years, built by various organisms over different periods. During the Permian period, reefs were built primarily by rugose and tabulate corals, groups that would go extinct at the end of the period, along with sponges, algae, and other organisms. These structures formed barriers along coastlines, creating lagoons and protecting shores from wave action. The reefs were biodiversity hotspots, supporting dense communities of life. Fish sheltered among the coral branches, crinoids, stalked echinoderms that looked like plants but were actually animals anchored themselves to the reef structure, their arms filtering food from the current. Brachiopods, with their two shells attached to hard surfaces or burrowed in sediment. Gastropods and bivalves crawled or sectioned themselves to the reef. The reef communities were complex food webs, primary producers, capturing sunlight, herbivores, grazing on algae, predators hunting the herbivores, scavengers, and decomposers, recycling dead material. The Permian extinction devastated these communities. The temperature and chemistry changes killed the coral and many other reef organisms. For millions of years afterward, reefs were largely absent or sparse. Eventually, new reef-building organisms evolved, and reefs returned, but they were never quite the same. Each major extinction resets the composition of reef communities, allowing different groups to take center stage. The life beneath the warm waters. Beneath the surface of Pangea's surrounding seas, life was diverse and strange by modern standards. Fish had diversified into many forms. Early bony fish swam in schools, feeding on plankton or hunting smaller fish. Sharks and their relatives patrolled deeper waters. Apex predators with keen senses and powerful jaws. Some fish had armor-like scales, protection against predators. Others were sleek and fast. The first marine reptiles were appearing, reptiles that had returned to the sea from land. These early forms were relatively primitive, still resembling their terrestrial ancestors, but they were beginning to adapt to aquatic life. Some had flipper-like limbs and streamlined bodies. Others retained more terrestrial features, perhaps spending time both on land and in water. These pioneers would give rise to the great marine reptile groups of the Mesozoic ichthyosaurs, plesiosaurs, mosasaurs, though those appeared after Pangea began breaking apart. Cephalopods were diverse. Besides ammonites, nautiloids swam through the water, their straight or coiled shells providing buoyancy. Belemnites, squid-like creatures with internal shells, were efficient predators. The oceans were as full of life as the best regions on land, perhaps more so, the water providing a more stable and forgiving environment than Pangea's harsh terrestrial interior. The changing atmosphere of the time. Earth's atmosphere during the Pangea era was different from today's. Oxygen levels fluctuated significantly over the Paleozoic and early Mesozoic. During the Carboniferous period, just before Pangea fully formed, oxygen levels were extremely high, perhaps 35% compared to today's 21%. This allowed insects to grow to enormous sizes. Giant dragonflies with 70-centimeter wingspans flew through the coal forests. By the Permian period, oxygen levels had dropped somewhat, though they remained higher than today. Carbon dioxide levels varied as well, affecting global temperature through the greenhouse effect. The massive volcanic eruptions that caused the Permian extinction released enormous amounts of carbon dioxide, warming the planet dramatically. The atmosphere contained other gases too, methane from wetlands, and possibly from warming oceans during the extinction, sulfur compounds from volcanoes. All the composition of the atmosphere affects everything: climate, ocean chemistry, the metabolism of organisms. Animals had to adapt to these changing conditions. Some groups developed more efficient respiratory systems. The changes in atmospheric composition during the Pangea era may have been selective pressures that drove the evolution of features we see in later groups, including the highly efficient respiratory systems of dinosaurs and birds. The shifts in global climate. Climate during Pangea's existence wasn't constant. It varied over millions of years, driven by factors like volcanic activity, asteroid impacts, changes in ocean circulation, and the configuration of the continents themselves. The early Permian period was relatively cool, with ice caps at the poles, unusual for most of the Paleozoic, but not unknown. As the period progressed, temperatures rose. By the late Permian, during the build-up to the extinction event, temperatures were much higher. The Triassic period, after Pangea was fully formed, saw continued warm conditions, though with some fluctuations. There were no ice caps. Even the poles were temperate, with forests rather than tundra or ice. The equatorial regions were extremely hot, possibly too hot for many organisms. Climate zones were strongly defined: tropical, subtropical, temperate, but no polar ice zones. The lack of ice caps meant sea levels were high, with shallow seas flooding large areas of the continents. These shallow seas, called epicontinental seas, created additional coastline and moderated climates in adjacent regions. The climate shifts affected which organisms could survive where, driving extinctions when conditions changed too rapidly for adaptation and creating opportunities when new habitats appeared. Understanding ancient climates helps us understand why certain organisms lived where they did and how they evolved. The circulation of air around one continent, with all land in one place and the ocean covering the rest. Atmospheric circulation patterns were very different from today. Air warmed at the equator would rise, creating low-pressure zones. This air moved toward the poles, cooling and descending at mid-latitudes, creating high-pressure zones. Return flow moved air back toward the equator near the surface. This basic pattern still exists today, but Pangea's configuration created extreme versions. The huge landmass disrupted normal circulation. Air masses moving across the supercontinent would dry out, having lost their moisture to earlier precipitation. The interior became a permanent high-pressure zone, hot and dry. Coastal regions received moisture from the ocean, but penetration inland was limited. The circulation patterns created intense seasonality. Summers brought some moisture as heated air over the continent created low pressure that drew in moist oceanic air. But this air dumped its rain on the coasts and foothills, leaving the interior dry. Winters reversed the pattern, with high pressure over the cold interior driving dry air outward. These patterns created the mega monsoons, seasonal wind reversals of enormous scale. bringing alternating wet and dry seasons to coastal regions, but leaving the interior perpetually parched. The mega monsoons of Pangea. Monsoons occur when temperature differences between land and ocean create pressure differences that drive seasonal wind reversals. Today, the Indian monsoon is the most dramatic example, bringing life-giving summer rains to South Asia. But Pangea's monsoons were far more extreme. The supercontinent was so large that seasonal heating and cooling created pressure differences of unprecedented scale. During summer, the land heated intensely, creating a vast low-pressure zone that drew in moist oceanic air. This air rushed onto the continent, carrying moisture that fell as torrential rains along the coasts. Rivers swelled, vegetation flourished, and life thrived. But the monsoon couldn't penetrate far inland. By the time air masses reached the interior, they'd been wrung dry. In winter, the pattern reversed. The land cooled, creating high pressure that drove air outward. The winds were dry, having originated over land, and they intensified the arid conditions along coasts. The seasonal reversals were dramatic, creating boom and bust cycles for ecosystems in monsoon-affected regions. Organisms had to adapt to alternating floods and droughts. Some plants evolved deciduous strategies, dropping leaves during dry seasons to conserve water. Animals migrated or entered dormancy. The mega monsoons shaped life in coastal Pangea, creating challenges and opportunities that drove evolutionary innovation. The patterns of drought and flood. Life in Pangea's monsoon zones required adaptability. The wet season brought abundance. Rivers flowed. Plants grew rapidly. Herbivores fattened. Predators feasted. But the dry season was harsh. Rivers shrank or disappeared. Vegetation withered, and survival became a struggle. Many organisms developed seasonal strategies. Some plants grew rapidly during wet seasons, produced seeds, then died back during dry seasons, surviving as seeds until rain returned. Others went dormant, their growth pausing until conditions improved. Animals migrated, following the rains to wherever moisture was available. Herds likely moved in seasonal patterns. Routes repeated year after year, generation after generation. Those unable to migrate had to survive in place. Some estivated, entering a state of dormancy during the driest months, their metabolism slowing to minimal levels. Others sought refuges, burrows, where humidity remained higher, shaded canyons where water persisted in pools. The seasonal patterns created ecological rhythms that structured entire ecosystems. Reproduction timed to coincide with the wet season, when food was abundant. Predators timed births so young would mature during periods of plenty. The seasonal extremes of Pangea created selective pressures that shaped evolution, favoring organisms with behavioral and physiological adaptations for surviving unpredictable conditions. The formation of the first superdeserts. Pangea's interior wasn't just dry. It was a true desert on a continental scale. Vast regions received virtually no rain year after year. Sand accumulated, blown by wind, into enormous dune fields. These weren't small deserts like we see today. They were super deserts, extending for thousands of kilometers, larger than any desert in modern times. The dunes marched across the landscape, driven by prevailing winds, burying everything in their path. In some regions, the sand piled hundreds of meters deep. Over time, as the climate shifted, or Pangea drifted through different latitudes, these dunes were buried and compressed, eventually lithifying into sandstone. Today, we can see the remains of Pangea's deserts in rock formations around the world. The Navajo sandstone in the southwestern United States, with its beautiful swirling cross-bedded layers, represents ancient sand dunes from Pangea's desert interior. Similar formations exist in other regions that were once part of the supercontinent. The patterns preserved in the rock, the cross-bedding created by dunes migrating over each other, the grain sizes indicating wind strength, tell us about wind directions and climate conditions 200 million years ago. The super deserts were harsh, nearly lifeless zones at the heart of the supercontinent, testaments to the climatic extremes that single continent configurations can create. The sand dunes that covered continents. Walking through places like Utah's Zion National Park or Arches National Park, you're surrounded by ancient sand dunes, turned to stone. The rock shows layers tilted at angles, curved in sweeping lines, the internal structure of dunes preserved for 200 million years. When these dunes were active, they were part of an enormous desert, covering much of what is now the western United States. Wind direction determined dune orientation, and by studying the cross-bedding patterns, geologists can determine which way winds blew during Pangea's time. The dunes weren't completely static. They migrated slowly, sand grains bouncing up the windward side, cascading down the leeward side, the dune walking across the landscape meter by meter, year by year. Occasionally, flash floods from distant mountains might have swept across the desert, temporarily transforming it. These floods left thin layers of finer sediment between the dune sands, creating the banded appearance we see in some formations. Rarely, life ventured into the dune fields. Fossil footprints have been found preserved in the ancient sandstones, showing where reptiles or early mammal-like creatures crossed the dunes, perhaps during cooler seasons or following rare rains. But mostly the dunes were barren, monuments to aridity, vast wastelands at Pangea's heart. The evidence found in ancient sandstone. Sandstone is more than just rock. It's a record. The grains themselves tell stories. Their size indicates the energy of the wind that transported them. Their roundness shows how far they traveled. Angular grains are local. Rounded grains have bounced along for great distances. The mineral composition reveals the source. What rocks were weathered to create the sand? The Navajo sandstone, for instance, contains grains that originated from mountains far to the east, transported across hundreds of kilometers by wind before being deposited in the dune fields. The cross-bedding patterns reveal wind directions, and therefore the climate patterns that created those winds. The presence of rare mudstone layers indicates occasional water, flash floods that interrupted the desert conditions briefly. The color of sandstone often indicates the presence of iron oxides, red sandstones formed in oxidizing conditions, typical of deserts. Occasionally, fossils are preserved in desert sandstones. These are rare because deserts aren't conducive to preservation. But when found, they're precious. Dinosaur footprints, rare skeletal remains, burrows created by organisms seeking shelter from the heat. Each fossil tells us about life that managed to survive or venture into these harsh environments. The ancient sandstones are textbooks, teaching us about Pangea's climate, geography, and the challenges life faced. The forests that once stood in the interior. Not all of Pangea's interior was desert. In some regions, perhaps along the paths of seasonal rivers, or in areas where the monsoon rains could penetrate, forests grew. These weren't the lush forests of the coasts, but hardy stands of conifers and other drought-adapted plants. They existed in a delicate balance, vulnerable to shifts in climate or rainfall patterns. Fossil evidence from these interior forests is rare, but tantalizing. Petrified wood, trees buried rapidly by sediment, their organic material replaced by minerals over millions of years, shows that substantial trees grew in what are now arid regions. The petrified forests of Arizona, for instance, contain logs up to 60 meters long, from trees that grew during the Triassic period when the region was part of Pangea's interior. These trees weren't growing in desert, but in a semi-arid environment, perhaps along river corridors where water was available. The presence of these forests indicates that conditions varied across Pangea's interior, that there were pockets and corridors where life could persist. The forests provided habitat for animals, insects, reptiles, early mammal-like creatures. They were oases in an otherwise harsh landscape, refuges where biodiversity concentrated. When climate shifts pushed the forests back, species trapped in shrinking forest patches might have faced extinction. while new species adapted to the expanding arid zones thrived. The fossilized trees of deep time. Petrified wood is remarkable. Trees turned to stone, preserved in such detail that growth rings, bark texture, and even cellular structure remain visible. The process requires specific conditions. The tree must be buried rapidly, protected from decay. Groundwater, rich in dissolved minerals, must permeate the wood, depositing silica or other minerals in the cell walls and cavities. Over millions of years, the original organic molecules are replaced atom by atom with minerals, creating a stone replica of the original structure. The result is beautiful, agate-like material with colors determined by the minerals involved. Iron oxides create reds and oranges. Manganese produces blacks and purples. The petrified logs scattered across Arizona's Petrified Forest National Park are from Araucarioxylon trees, an extinct genus of conifer related to modern monkey puzzle trees. These grew during the Triassic period, about 225 million years ago, when the region was part of Pangea. The forests were periodically buried by floods, which preserved the logs. Studying these fossils reveals information about the trees' growth rates, the climate they experienced, and even damage from insects or disease. Petrified wood provides a direct window into ancient forests, allowing us to literally hold pieces of Pangea's vegetation in our hands, examining structures that grew when the supercontinent still existed. The early mammal-like reptiles. Before dinosaurs, before true mammals, there were synapsids, often called mammal-like reptiles, because they share characteristics with both groups. These creatures dominated terrestrial ecosystems during the Permian period, the height of Pangea's unity. They ranged from small insectivores to massive herbivores to fearsome predators. Dimetrodon is the most famous, with its distinctive sail, a structure of elongated vertebrae covered in skin, possibly used for thermoregulation or display. It was a top predator of its time, hunting other synapsids and early reptiles with its powerful jaws and sharp teeth. Moschops was a barrel-bodied herbivore, pig-sized and robust, browsing on tough vegetation. Gorgonopsids were saber-toothed predators that lived late in the Permian, just before the extinction. They had large canine teeth and were likely efficient hunters. The synapsids show progressive development of mammalian characteristics. Earlier forms were more reptilian, but later groups developed features like differentiated teeth, secondary palates, allowing them to breathe while eating, and possibly hair and endothermy. The Permian extinction hit synapsids hard. Many lineages vanished, but the survivors gave rise to the therapsids, which eventually evolved into true mammals during the Mesozoic, though they would remain small and relatively inconspicuous until after the dinosaurs' reign ended. The dominant life before dinosaurs. The world of Permian Pangea was ruled by synapsids, not the dinosaurs that would come later. The ecosystems were complex and balanced. Large herbivores like dinocephalians and parasaurs browsed on plants, processing tough vegetation with specialized teeth and powerful jaws. Mid-sized herbivores filled different niches, feeding on different plant types or at different heights. Predators ranged from small insectivores to apex carnivores. The food webs were as intricate as modern ones, with decomposers, scavengers, and parasites filling supporting roles. Some synapsids show evidence of complex behaviors. Burrows suggest underground shelters. Trackways show social behavior, multiple individuals traveling together. Bone beds containing many individuals might indicate herding, though this is debated. The diversity was impressive. Hundreds of species evolved during Pangea's Permian period, filling every terrestrial niche. This was a fully realized biosphere, as successful and complete as any that existed before or since. Then the Permian extinction ended it all. The synapsid-dominated world vanished almost completely. The few survivors found themselves in a devastated landscape. Ecosystems collapsed, most niches empty. The recovery would take millions of years, and when it was complete, the world would look very different, with new groups rising to dominance. The archosaurs, ancestors of dinosaurs and crocodiles, seizing the opportunity the extinction created. The great predators of the Permian, the apex predators of Permian Pangea, were formidable hunters. Gorgonopsids were particularly impressive, dog-sized to bear-sized carnivores with enormous canine teeth. Their skulls show powerful jaw muscles and eyes positioned for binocular vision, suggesting they were active hunters rather than scavengers. Some had canines 20 centimeters long, true sabers. They likely hunted the large herbivores of the time, using their teeth to deliver devastating bites to vulnerable areas like the throat or belly. The presence of large predators indicates healthy prey populations and functioning ecosystems. Predators sit atop food pyramids, requiring large numbers of herbivores below them, which in turn require abundant plant life. The fact that predators this large could exist tells us that Pangea's ecosystems, at least in the more hospitable regions, were productive enough to support complex food webs. Some evidence suggests these predators might have been endothermic, warm-blooded. Bone structure and posture suggest active metabolism. If true, this would be an early evolution of endothermy, millions of years before mammals or dinosaurs. The Gorgonopsids, when extinct in the Permian extinction, no close relatives survived. They represent an evolutionary experiment that ended in catastrophe, a lineage that might have continued dominating if fate, in the form of volcanic eruptions and climate change, hadn't intervened. The ecosystems of a changing world. Ecosystems during Pangea's time weren't static. They changed continuously, responding to climate shifts, continental drift, and evolution. The early Permian ecosystems, with diverse synapsids and extensive coal swamps, gave way to drier late Permian ecosystems, dominated by seed plants and drought-adapted animals. After the extinction, Triassic ecosystems were impoverished, with low diversity and simplified food webs. Recovery was gradual. Pioneer species colonized empty niches, predator-prey relationships re-established. Slowly, complexity returned. The Triassic period saw the rise of new groups that would dominate the Mesozoic: dinosaurs, pterosaurs, marine reptiles. These groups evolved in a world still recovering from catastrophe, taking advantage of empty ecological spaces. The ecosystems of Pangea demonstrate that life is resilient but not invulnerable. Severe disruptions can devastate even well-established systems. Recovery is possible, but takes millions of years. The patterns we see in Pangea's ecosystems, the rise and fall of dominant groups, the filling of niches, the response to environmental change, are patterns that repeat throughout Earth's history, universal principles of ecology and evolution, playing out across geological time. The largest extinction in Earth's history, the Permian Triassic extinction event, 252 million years ago, was Earth's closest brush with total annihilation of complex life. The extinction unfolded over perhaps 60,000 years, geologically rapid, but still a long catastrophe. Multiple causes converged to create perfect conditions for mass death. The Siberian Traps eruptions, one of the largest volcanic events in Earth's history, covered an area the size of Europe with basalt lava and released enormous quantities of gases. Carbon dioxide caused global warming of perhaps 10 to 14 degrees Celsius. Sulfur dioxide created acid rain. The warming initiated feedback loops. Methane released from warming oceans added more greenhouse warming. Ocean temperatures rose above 30 degrees Celsius in some regions, reducing dissolved oxygen and creating anoxic conditions. Marine life suffocated. On land, temperatures exceeded lethal thresholds for many organisms. Arid conditions intensified. The extinction was global and indiscriminate. 96% of marine species, 70% of terrestrial vertebrates, and 83% of insect genera died. Entire orders and classes vanished. The world's ecosystems collapsed completely. The extinction reset life on Earth, creating conditions for new groups to evolve and dominate. Without this extinction, the dinosaurs might never have risen. The mammalian lineage might have ended. The world we know might never have come to be. The Great Dying at the end of the Permian. The Permian extinction has been called the Great Dying, a name that captures its scale and horror. For organisms living through it, the world became progressively more hostile. Temperatures rose year after year. Droughts intensified. The air itself may have become toxic in some regions. Sulfur compounds and other volcanic gases, making breathing difficult. In the oceans, warming reduced oxygen levels. Dead zones expanded. Coral reefs died, their skeletons dissolving in acidifying waters. Fish and invertebrates suffocated. On land, forests withered. Herbivores starved as plant life declined. Predators followed, losing their prey base. The extinction wasn't a single event, but a cascade of ecosystem collapses, one failure triggering others in a domino effect. Some regions were hit harder than others. Tropical zones, already hot, became uninhabitable as temperatures soared. Polar regions, with cooler starting temperatures, might have remained tolerable longer, but ultimately, nowhere escaped. The fossil record shows the progression, abundant and diverse life, in pre-extinction layers, then a sudden collapse in diversity, followed by meters or tens of meters of rock, with almost no fossils at all. This barren interval, called the survival interval, represents the nadir, when life was at its lowest ebb. Very slowly, fossils reappear in younger rocks. The recovery had begun, but it would take 10 million years for ecosystems to fully recover their former complexity. The oceans that lost their oxygen. One of the killing mechanisms of the Permian extinction was oceanic anoxia, the loss of dissolved oxygen in seawater. Warm water holds less oxygen than cold water. So as ocean temperatures rose, oxygen levels dropped. This would have been bad enough, but additional factors worsened the situation. Increased weathering on land, driven by warmer and possibly wetter conditions, delivered more nutrients to the oceans. These nutrients fertilized algae blooms. When the algae died and sank, bacteria consumed them, using up oxygen in the process. This created expanding zones of oxygen-depleted water, particularly in deeper oceans and restricted basins. Anoxic conditions spread, killing marine life, unable to tolerate low oxygen. Some regions developed oceania, waters not only depleted in oxygen, but containing hydrogen sulfide, a toxic gas produced by bacteria under anoxic conditions. These poisonous waters expanded, potentially reaching into shallow zones, where most marine life concentrated. The ocean became stratified, a thin oxygenated layer at the surface, toxic anoxic layers below. The extinction killed organisms across all depths. Even surface dwellers were affected as their habitat shrank. The anoxic oceans took millions of years to recover, the oxygen slowly returning as temperatures eventually declined and ocean circulation reestablished. The black shales deposited during this period, rich in organic carbon preserved under anoxic conditions, testify to the ocean's dead state. The heat that scorched the Earth. Temperature during the late Permian extinction rose to levels nearly lethal for life. Estimates suggest global average temperatures reached 35 to 40 degrees Celsius, far hotter than today's 17 degrees. But averages mask extremes. Tropical regions likely experienced temperatures exceeding 50 degrees during summer, hot enough to kill most animals through heat stress. Even at night, temperatures remained high. There was no escape. On land, organisms sought shade, burrows, or water, but these refuges were limited. Many simply couldn't cope. Heat disrupts physiology. Enzymes denature. Proteins unfold. Cellular processes fail. Endothermic animals, which maintain constant body temperature, struggle in extreme heat because they can't dissipate metabolic heat fast enough. Ectothermic animals, which rely on external temperatures, are constrained by upper thermal limits. The heat was relentless, sustained over thousands of years, giving evolution no time to adapt. The fossil record shows extinctions concentrated in low latitudes, where heat was most extreme. Polar regions, relatively cooler, had higher survival rates. Some organisms retreated poleward, tracking tolerable temperatures as climate zones shifted. But polar regions have limited area and resources, creating bottlenecks. Many species went extinct, even if some individuals survived the heat. Their populations reduced below viable levels. The heat of the Permian extinction shows how narrow the habitable temperature range for complex life is. A few degrees of warming causes stress. 10 degrees or more causes mass death. The eruption of massive volcanoes. The Siberian traps represent one of the largest volcanic events Earth has experienced. Over about 2 million years, with peak activity around the extinction event, basaltic lava flooded out of fissures, covering an area exceeding 4 million square kilometers, nearly the size of Australia, with lava flows up to 3 kilometers thick in places. The eruptions weren't explosive like Krakatoa or Mount St. Helens, but effusive. Lava poured out continuously, spreading across the landscape. But the lava itself wasn't the main killer. More deadly were the gases released. Each cubic kilometer of basalt released enormous quantities of carbon dioxide, sulfur dioxide, chlorine, and other gases. The total erupted volume was perhaps 3 million cubic kilometers, meaning trillions of tons of gases entered the atmosphere. Sulfur dioxide created sulfuric acid aerosols that reflected sunlight, causing short-term cooling, even as carbon dioxide drove long-term warming. Acid rain fell globally, acidifying soils and waters. The eruptions may have ignited coal deposits, releasing additional greenhouse gases. Some models suggest the eruptions even burned through organic-rich sediments, releasing methane. The volcanic activity lasted for the entire duration of the extinction and beyond, continually pumping greenhouse gases into the atmosphere, preventing recovery, driving the climate into a sustained hothouse state. The Siberian traps eruptions demonstrate that volcanic catastrophes don't have to be explosive to be deadly. Persistent flood basalt eruptions can alter climate enough to trigger mass extinctions. The Siberian traps and their firestorms. The Siberian traps weren't just lava and gas. They may have ignited vast firestorms. When the eruptions burned through coal seams and organic-rich sediments, they released not only greenhouse gases, but also combustion products. Soot and ash darkened the skies. If the organic material burned on a large scale, the smoke might have created a nuclear winter effect, temporarily cooling the planet, even as greenhouse gases accumulated for later warming. Some geological evidence supports massive burning. Layers of soot and charcoal appear in sediments from the extinction interval, not just near the Siberian traps, but globally, suggesting widespread wildfires. The burning may have been triggered by volcanic activity igniting vegetation, or by lightning in the disturbed atmosphere, or by the combustion of underground coal. The combination of volcanic winter from particulates and later greenhouse warming from gases created a climate roller coaster, rapid oscillations that stressed ecosystems repeatedly. Organisms adapted to cold were killed by warming. Those adapted to warmth were killed by cooling. The instability may have been as deadly as the extremes, giving life no chance to stabilize or adapt. The Siberian traps demonstrate that Earth's most catastrophic events involve multiple interacting factors. It wasn't just volcanoes or just climate change, but a complex cascade of environmental disruptions that pushed the planet past tipping points. The sky darkened by ash and smoke. Imagine the sky during the height of the Siberian traps eruptions. Instead of blue, a pall of gray and brown, volcanic ash and sulfate aerosols blocking the sun. The light reaching the surface would be dim, reddish, eerie. Photosynthesis would have been impaired, plants struggling to produce energy with reduced sunlight. This would affect entire food webs, herbivores starving as plants declined, predators following as their prey disappeared. The darkness might have lasted years or decades during peak eruption phases, though the full volcanic episode spanned hundreds of thousands of years with varying intensity. The ash fell globally, carried by winds and atmospheric circulation. Layers of volcanic ash appear in rocks worldwide from this period, evidence of the eruption's global reach. The ash would have contaminated water sources, covered vegetation, made breathing difficult. Combined with the acid rain from sulfur compounds, the surface environment became increasingly hostile. Some organisms might have survived in refuges, deep burrows, underwater, in polar regions less affected by the fallout. But most faced impossible conditions. The darkness itself, while temporary compared to the warming, delivered an immediate shock to ecosystems. Primary production collapsed. This triggered rapid extinctions up the food chain. By the time the skies cleared and sunlight returned fully, the damage was done. Ecosystems had collapsed, and the survivors faced a different world, one growing warmer, more acidic, less hospitable with each passing millennium. The collapse of ancient ecosystems. Ecosystems are networks of relationships, predator and prey, pollinator and plant, decomposer and detritus. Remove enough components, and the network unravels. The Permian extinction removed components wholesale. When the large herbivores died, predators that depended on them followed. When plants declined, herbivores starved. When coral reefs died, all the species that depended on them, fish, invertebrates, the entire reef community, vanished. The collapse cascaded through every level. Even organisms that survived the initial stresses faced secondary extinctions as their food sources or habitats disappeared. The extinction created what ecologists call an ecological meltdown, the sequential failure of interconnected systems. Some ecosystems collapsed completely, leaving barren landscapes or empty oceans. Others simplified dramatically, reduced to just a few hardy species, eking out survival in marginal conditions. The fossil record shows this progression. Before the extinction, diverse assemblages of many species. During the extinction, rapid loss of diversity. After the extinction, sparse assemblages of a few generalist species, the disaster taxa that could survive in degraded conditions. These survivors were often opportunists, able to tolerate wide ranges of conditions, reproduce quickly, and exploit disturbed environments. They weren't the most impressive or specialized organisms, but they were tough and adaptable. They inherited the Earth simply by surviving when others couldn't. From these humble survivors, life would slowly rebuild its complexity, the slow recovery of life. After the extinction, Earth was empty, not literally. Millions of organisms still lived, but ecologically, niches that had been filled for millions of years were vacant. Ecosystems were simplified to a few species. Diversity was a fraction of what it had been. Recovery began slowly. The first phase involved disaster species, organisms adapted to disturbed conditions, spreading widely. These pioneer species weren't diverse or specialized, but they could survive in the harsh post-extinction environment. They formed simple, low-diversity ecosystems, basic food webs with few links. Gradually, as conditions improved, volcanic activity declining, climate stabilizing, vegetation returning, opportunities appeared for diversification. New species evolved to exploit underutilized resources. Survivors of the extinction adapted to new roles. Empty niches began filling. The recovery took millions of years. For the first 5 million years of the Triassic period, diversity remained low. Ecosystems were simple, vulnerable. Slowly, complexity increased. New groups evolved. The archosaurs began diversifying, leading eventually to dinosaurs. Marine reptiles entered the oceans. In the seas, new families of mollusks, fish, and other organisms evolved to replace extinct groups. By 10 million years after the extinction, Ecosystems had regained much of their former complexity, though with entirely different casts of characters. The recovery demonstrates life's resilience, but also shows how long recovery takes. Extinction is quick. Restoration is slow. The dawn of a new age. The Triassic period emerged from the ashes of the Permian, the new beginning for life on Earth. The world was still hot, still harsh, Pangea still intact, but life was adapting, evolving, filling the spaces the extinction had cleared. New groups appeared that would shape the future. The archosaurs split into multiple lineages. One would lead to crocodilians, another to pterosaurs, the first vertebrates to achieve powered flight, and one would lead to the dinosaurs, which would come to dominate terrestrial ecosystems for the next 160 million years. The therapsids, survivors from the synapsid lineage, evolved into the first true mammals, though they would remain small and mostly nocturnal for the duration of the dinosaur age. In the oceans, marine reptiles diversified, experimenting with different body plans for aquatic life. The ichthyosaurs appeared, dolphin-shaped and efficient. The Triassic was a time of experimentation, evolution testing new forms, new strategies. Many lineages appeared then went extinct, failed experiments. But some succeeded spectacularly. The foundations of the Mesozoic world, the age of dinosaurs, were laid during the Triassic recovery. Pangea's harsh conditions created selective pressures that shaped these new groups, preparing them for the success they would achieve after the supercontinent broke apart and conditions moderated. The rise of the first dinosaurs. Dinosaurs appeared during the Triassic period, perhaps around 230 million years ago, as small bipedal carnivores. Early dinosaurs like Eoraptor and Herrerasaurus were modest creatures, a meter or two long, agile predators, hunting smaller animals. They weren't dominant. Larger archosaurs and surviving synapsids still controlled most ecological niches, but dinosaurs had certain advantages. Their upright posture, with legs positioned directly beneath their bodies, was more energy efficient than the sprawling stance of other reptiles. Their respiratory system, possibly including air sacs like modern birds, made them efficient breathers. These advantages weren't immediately decisive, but they positioned dinosaurs for future success. A second extinction event, at the end of the Triassic, smaller than the Permian catastrophe, but still significant, removed many competitors. Dinosaurs survived and diversified rapidly into the vacant niches. By the start of the Jurassic period, they had become the dominant large land animals, a position they would hold until the asteroid impact 66 million years ago ended their reign. The early dinosaurs of Pangea were harbingers of what was to come, pioneer species that would give rise to the spectacular diversity of the Mesozoic, the giants, the hunters, the armored and horned forms that continue to capture our imagination today. The Jurassic world begins to form. The transition from Triassic to Jurassic, about 201 million years ago, marked another turning point, an extinction event caused by volcanic activity associated with the initial breakup of Pangea, removed many remaining Triassic groups. In the aftermath, dinosaurs radiated explosively, diversifying into the major groups that would characterize the Mesozoic. Sauropods, the long-necked giants, evolved and began their march toward enormous sizes. Sauropods diversified into numerous forms, from small swift hunters to massive predators. Ornithischians, the bird-hipped dinosaurs, appeared, beginning their own diversification that would eventually produce armored ankylosaurs, horned ceratopsians, and duck-billed hadrosaurs. At the same time, Pangea was fracturing. The supercontinent that had existed for 60 million years was pulling apart, rifts opening in its crust, the Atlantic Ocean beginning to form. The breakup happened slowly, taking tens of millions of years, but its effects were profound. As continents separated, ocean circulation changed. The vast interior desert began to shrink as coastlines expanded and moisture penetrated further inland. Climate moderated. Rainfall increased. The Jurassic world was wetter, greener, more hospitable than Pangea's peak. These improved conditions allowed the dinosaurs to flourish, spreading across all continents, reaching sizes and diversity that defined the age. The cracks that split the supercontinent, Pangea, began breaking apart during the Jurassic period, roughly 200 million years ago. The process wasn't sudden. Continents don't shatter like glass. Instead, rifts formed gradually. Weaknesses in the crust, where tectonic forces pulled the landmass in different directions. The rifting began in several locations, nearly simultaneously. One rift opened between North America and Africa, eventually becoming the Central Atlantic. Another formed between Africa and South America, creating the South Atlantic, though this ocean wouldn't fully open until much later. A third rift separated Africa from India, Madagascar, and Antarctica. These rifts started as valleys, low-lying areas where the crust was stretching and thinning. Volcanic activity accompanied the rifting, magma rising through the weakened crust, erupting in long fissures. Eventually, the rifts dropped below sea level, and ocean water flooded in, creating narrow seaways. These seaways widened over millions of years. As seafloor spreading continued, the continents pushed apart by new crust, forming at mid-ocean ridges. The breakup of Pangea was driven by mantle convection, hot material rising beneath the supercontinent, pushing it apart from below. The fragmentation would continue through the Mesozoic and Cenozoic eras, eventually creating the continental configuration we know today. Though the process isn't finished, the continents continue drifting even now. The rifting of Pangea's core. The initial rifts that split Pangea created dramatic landscapes. Picture vast valleys, tens of kilometers wide, floors dropping thousands of meters below the surrounding plateau. Volcanic peaks lined the rift margins, regularly erupting and adding to the chaos. Rivers drained into these valleys, creating lakes that filled and evaporated, leaving salt deposits. As the rifts deepened and widened, they eventually breached sea level, allowing ocean water to flood in. Initially, these were probably shallow, restricted seaways, more like enormous bays than true oceans. The water was likely very salty, high evaporation, in a warm climate, concentrating dissolved minerals. Over time, the rift valleys widened into ocean basins. New seafloor formed at spreading ridges, running down their centers, pushing the continents further apart. The Atlantic Ocean was born this way, starting as a narrow seaway between continents barely separated, widening centimeter by centimeter, year by year, until it became the vast ocean we know today. The process took 150 million years and continues still. The Atlantic grows wider every year as Europe and North America move apart. Similar processes opened other oceans. The Tethys Sea, which had indented Pangea's eastern coast, widened and eventually closed again as India drifted north and collided with Asia. The rifting created the geography of the modern world, the ocean basins and continental positions that define our planet. The formation of new oceans. As Pangea broke apart, new oceans formed in the growing gaps between continents. The Atlantic Ocean is the largest and most significant of these. It began as a narrow rift valley during the Jurassic period, slowly widening through the Cretaceous and Cenozoic. Today, it's thousands of kilometers wide, still growing at about 2 to 3 centimeters per year. The Mid-Atlantic Ridge, an underwater mountain chain running down the ocean's center, marks where new seafloor continues forming. The Indian Ocean formed as India separated from Africa and Antarctica, drifting northward. The Arctic Ocean opened as continents surrounding the North Pole moved apart. These new oceans transformed Earth's climate and ecosystems. Ocean currents could now flow around and between continents, rather than being restricted to circling Pangea. This improved heat distribution, moderating temperatures. Coastal regions expanded enormously, creating new habitats and milder climates. The increased area of shallow seas and continental margins provided environments for marine life to diversify. The biological effects were profound. Evolution accelerated as isolated populations diverged. The Cretaceous and Cenozoic eras saw explosive diversification of many groups, both on land and in the oceans, driven in part by the new geography created by Pangea's breakup. The formation of new oceans demonstrates how geology and biology are intertwined, continental movements shaping the course of evolution. The birth of the Atlantic Basin. The Atlantic Ocean's formation began during the Jurassic period, around 180 million years ago, when rifting opened between North America and Africa. The initial rift created a narrow seaway, perhaps similar to the modern Red Sea. Volcanic islands lined the margins. The water was warm, tropical. The climate around the infant ocean hot and humid. As seafloor spreading continued, the ocean widened. By the Cretaceous period, the Atlantic was a significant ocean, though still narrower than today. Shallow seas covered the continental margins, creating extensive marine habitats. Sea levels were high during much of the Cretaceous, higher than today, flooding low-lying areas of the continents. The Atlantic's opening had major effects on global circulation. The circumglobal current that had flowed around Pangea was disrupted. New current patterns developed, redistributing heat differently. The climate shifted, generally becoming warmer and more equitable. The Atlantic continues opening today. GPS measurements show North America and Europe separating at about 2.5 centimeters per year, roughly the rate your fingernails grow. Over millions of years, this adds up. Eventually, perhaps 200 million years from now, the Atlantic may begin closing as plate tectonic forces reverse, the continents moving back together. The oceans that separate us now are temporary features, gaps between continents in their endless dance across the planet's surface. The breaking apart of Laurasia and Gondwana. Pangea first split into two major landmasses, Laurasia in the north and Gondwana in the south, separated by the growing Tethys Sea. This division occurred during the Jurassic period. Laurasia included what would become North America, Europe, and Asia. Gondwana included South America, Africa, India, Australia, and Antarctica. These two supercontinents didn't remain intact. Gondwana began fragmenting during the Cretaceous period. First, Africa separated from South America, the South Atlantic opening between them. India broke away, beginning its dramatic northward journey that would eventually result in its collision with Asia and the rise of the Himalayas. Madagascar split from Africa. Australia separated from Antarctica, which remained positioned over the South Pole. Laurasia also fragmented. North America separated from Europe, the North Atlantic opening between them. The Tethys Sea, which had separated Laurasia and Gondwana, eventually closed as Africa moved north toward Europe. The continents resulting from Gondwana's breakup carried distinctive biota, the legacy of their time connected. The southern continents share plant and animal groups not found in the north, evidence of their ancient unity. Fossils of the same species appear on continents now separated by thousands of kilometers of ocean, proof they were once joined. The breakup of Laurasia and Gondwana created the continental configuration that would evolve into our modern world. The slow drift of the continents. After Pangea broke apart, the fragments drifted slowly across the globe, carried by the movement of tectonic plates. India's journey is particularly dramatic. It separated from Gondwana about 140 million years ago and moved northward at rates reaching 15 centimeters per year, fast for continental drift. Its collision with Asia, about 50 million years ago, was a slow-motion crash that continues today. The Himalayas, still rising as India pushes into the Asian continent. Australia separated from Antarctica about 45 million years ago and has been drifting north ever since, currently moving towards Southeast Asia at about 7 centimeters per year. South America and Africa, once joined, now sit on opposite sides of the Atlantic, separated by 5,000 kilometers of ocean. The continents continue their journeys. Africa is moving north, slowly closing the Mediterranean Sea. In 50 million years, it may collide with Europe, creating new mountains. The Atlantic continues widening, while the Pacific shrinks, its edges consumed at subduction zones. The continents never stop moving, never settle into permanent positions. The map we know is temporary, one frame in an ongoing process that has continued for billions of years and will continue for billions more until Earth's internal heat dissipates enough that plate tectonics cease. The continents we know begin to form. The continents we're familiar with: North America, South America, Europe, Africa, Asia, Australia, Antarctica, emerged from Pangea's breakup and continued evolving through the Mesozoic and Cenozoic eras. They weren't instantly recognizable. The continents had different shapes, different positions, different climates than today. North America was separated from South America until a few million years ago, when the Isthmus of Panama formed, connecting them. Australia was positioned further south, connected to Antarctica, until 45 million years ago. India was an island continent for tens of millions of years before colliding with Asia. The continents reached their current positions relatively recently in geological terms. Europe and Asia, though long connected, were separated by shallow seas during various periods. Africa's current position, nearly connecting to Eurasia at the Suez, is recent. For most of the Cenozoic, a seaway separated them. The modern map is the result of 180 million years of continental drift following Pangea's breakup, but it's not the final configuration. The continents will continue moving, their positions in 50 or 100 million years different from today's, part of the ongoing cycle of continental assembly and dispersal. The migration of life across the divides. As continents separated, the organisms living on them faced new challenges and opportunities. Populations that had been continuous were divided, isolated on separating landmasses. This isolation drove evolution. Separated populations diverged, adapting to their local conditions, eventually becoming distinct species. This explains why different continents have distinctive faunas. Marsupials, which once lived worldwide, are now found primarily in Australia and South America, continents that were connected through Antarctica long after they separated from other landmasses, allowing marsupials to persist there while going extinct elsewhere. Certain plant families are distributed across southern continents, evidence of Gondwana's ancient unity. While some groups were isolated by continental separation, others managed to cross the growing oceans. Birds could fly across, colonizing new landmasses. Some reptiles and small mammals might have rafted on floating vegetation, drifting across narrow seaways to reach new continents. Marine organisms weren't constrained by continental positions, though ocean currents and temperature barriers created their own biogeographic patterns. The migration and isolation of life following Pangea's breakup created the modern distribution of species, the puzzle of biogeography that helped early naturalists, including Darwin, develop the theory of evolution. The patterns make sense only in the context of moving continents and deep time. The isolation of new ecosystems. When continents separated, the isolated landmasses became evolutionary laboratories, each developing its own distinctive ecosystem. Australia, isolated for 45 million years, evolved unique marsupial fauna, kangaroos, koalas, wombats, filling niches that placental mammals occupy on other continents. South America, isolated for much of the Cenozoic, developed distinctive mammals, including sloths, armadillos, and unique predators like saber-toothed marsupials. When the Isthmus of Panama formed 3 million years ago, reconnecting South and North America, the two long isolated faunas mixed in what's called the Great American Interchange. Species from North America, big cats, bears, deer, moved south. South American species, armadillos, Opossums, porcupines, moved north. The interchange favored northern species, and many southern groups went extinct, unable to compete with the invaders. Madagascar, separated from Africa for 88 million years, evolved extraordinary uniqueness. Lemurs, unique carnivores, bizarre tinrex, a miniature evolutionary experiment, isolated on an island continent. New Zealand, separated from other land masses for even longer, had no terrestrial mammals except bats, until humans arrived, instead evolving flightless birds that filled mammalian niches. These isolated ecosystems demonstrate evolution's creativity and the importance of geography in shaping life. Isolation allows divergence, connection allows competition and exchange. The changing climate of the Mesozoic. The climate, during the breakup of Pangea and through the Mesozoic era, was generally warmer than today. There were no polar ice caps for most of this time. Dinosaurs lived in polar regions, though exactly how they survived the months-long darkness of polar winter remains debated. The warm climate was driven by higher carbon dioxide levels and different ocean circulation patterns. As Pangea broke apart and new oceans formed, circulation changed, redistributing heat more effectively. The interior deserts shrank, replaced by more moderate climates, as moisture from the expanding ocean coasts penetrated inland. The Cretaceous period, the final period of the Mesozoic, was particularly warm. The Cretaceous thermal maximum saw tropical temperatures reaching the Arctic Circle. Sea levels were extremely high, flooding large areas of the continents. These warm, wet conditions promoted lush vegetation, which supported the diverse and numerous dinosaur populations. But climate wasn't uniform. There were variations, cooler and warmer periods, wetter and drier intervals. The end of the Cretaceous saw gradual cooling, though temperatures remained warmer than today. This climate change may have stressed dinosaur populations even before the asteroid impact delivered the final blow. The Mesozoic climate demonstrates that Earth's baseline state, without human influence, can be dramatically warmer than the relatively cool conditions of the recent past. The forests that spread across the divided lands. As Pangea broke apart and climate moderated, forests spread across the newly separated continents. The Mesozoic forests were different from modern ones, dominated by conifers, cycads, and ferns, rather than flowering plants, at least until the Cretaceous, when angiosperms appeared and quickly diversified. The Jurassic forests were lush, dominated by conifers like araucarias and podocarps, with an understory of ferns and cycads. These forests supported the herbivorous dinosaurs, sauropods browsing the canopy, smaller ornithischians feeding on lower vegetation. In the Cretaceous, flowering plants appeared and revolutionized terrestrial ecosystems. They grew faster than gymnosperms, colonized disturbed areas quickly, and formed new relationships with pollinating insects. By the late Cretaceous, angiosperms dominated many environments, and herbivorous dinosaurs had adapted to feed on them, some developing specialized teeth and jaws for processing flowering plants. The forests of separated continents began diverging, each landmass developing its own distinctive flora as isolation allowed evolutionary divergence. The forest types varied with latitude and local conditions: tropical rainforests near the equator, temperate forests at mid-latitudes, and even polar forests in high latitudes, though these were deciduous, dropping leaves during the dark winter months. The forests shaped by Pangea's breakup created the template for modern ecosystems, the basic patterns we see today. The rise of the dinosaurs. In a new world, the dinosaurs flourished in the world following Pangea's breakup. The more moderate climate, expanded coastlines, and diverse environments allowed them to diversify spectacularly. They adapted to every available niche: giant sauropods browsing treetops, armored ankylosaurs defending themselves with tail clubs, swift hunters like Velociraptor working in packs, massive predators like Tyrannosaurus rex dominating food chains. Some dinosaurs evolved feathers, Some developed elaborate crests and horns. Others grew armor and spikes. They ranged from chicken-sized to whale-sized, from herbivores to carnivores to omnivores. The dinosaurs dominated terrestrial ecosystems for over 100 million years, one of the most successful groups of animals ever to exist. Their success was partly due to timing. They evolved in the aftermath of the Triassic extinction and radiated into empty niches, and partly due to adaptations that made them efficient and competitive. But their success was also enabled by the changing world created by Pangea's breakup, the improved climate, the diverse environments of separated continents, the opportunities created by isolation and dispersal, all contributed. The dinosaurs' story is inseparable from the story of the continents. Geology and biology intertwined. When the asteroid struck 66 million years ago, ending the Cretaceous period, the dinosaur age ended. But their legacy continues in birds, the living dinosaurs that survived the catastrophe. The patterns of continental movement. The patterns of continental movement following Pangea's breakup reveal underlying principles. Continents don't move randomly. They're driven by mantle convection, by the push of spreading ridges, and the pull of subducting slabs. The Atlantic Ocean opened because a mantle upwelling beneath Pangea pushed the continents apart. The Pacific Ocean shrinks because its edges are being consumed at subduction zones faster than new crust forms at its central ridges. India moved north rapidly because it was being pulled by a subducting slab descending beneath Asia. These patterns repeat throughout Earth's history. Continents assemble into supercontinents, creating a concentrated mass of crust that acts like insulation, trapping heat from the mantle below. Eventually, the trapped heat creates an upwelling that rifts the supercontinent apart. The fragments drift away, eventually colliding with other continents, assembling into a new supercontinent in a different configuration. This cycle, called the supercontinent cycle, repeats roughly every 400 to 600 million years. Pangea was just one iteration. Before it came Rodinia, before that Columbia, before that other supercontinents, whose names we don't know. After Pangea came the dispersed continents we know today. In the future, they'll assemble again into a new supercontinent, repeating the ancient pattern. The magnetic stripes on the ocean floor, one of the key pieces of evidence that confirmed plate tectonics and continental drift, came from an unexpected source: the magnetic properties of seafloor rocks. As magma erupts at mid-ocean ridges and cools, iron-bearing minerals align with Earth's magnetic field, recording its direction. Earth's magnetic field reverses irregularly, switching north and south poles every few 100,000 years. This creates a pattern. Rocks formed during periods of normal polarity have magnetic fields pointing one direction. Those formed during reversed polarity point the opposite way. Scientists mapping the seafloor discovered symmetrical patterns of magnetic stripes running parallel to mid-ocean ridges, alternating normal and reversed polarity. The pattern is the same on both sides of the ridge, showing that new seafloor forms at the ridge and moves away symmetrically. This was the smoking gun, the definitive proof of seafloor spreading. The magnetic stripes provided not only evidence, but also a timeline. By dating the reversals and measuring stripe widths, scientists could calculate spreading rates, how fast continents were moving apart. Different ridges show different rates. The East Pacific rise spreads quickly, creating wide stripes. The Mid-Atlantic ridge spreads more slowly, producing narrower stripes. The magnetic stripes revolutionized geology, providing irrefutable evidence that continents move and allowing precise reconstruction of their past positions. The discovery of plate tectonics. The theory of plate tectonics came together in the 1960s, synthesizing decades of observations into a comprehensive framework. Continental drift, proposed by Wegener in 1912, had explained the distribution of fossils and the fit of coastlines, but lacked a mechanism. Seafloor spreading, proposed in the 1960s, provided that mechanism. New ocean crust, forming at ridges, pushing continents apart. The magnetic stripes confirmed it. Earthquake patterns showed plate boundaries. Deep ocean trenches marked subduction zones, where old crust descends back into the mantle. Transform faults showed plates sliding past each other. Volcanic chains showed hotspots, where plumes of hot mantle material rise. Suddenly, everything made sense. Earthquakes occur at plate boundaries, because that's where stress accumulates. Volcanoes form where subducting plates melt, or where hotspots penetrate the crust. Mountains rise where continents collide. Ocean basins open where rifts form. The theory explained the present and the past. It allowed reconstruction of ancient continental positions by reversing the movements. It predicted future configurations by extrapolating current motions. Plate tectonics unified geology, turning it from a descriptive science into one with predictive power. It stands alongside evolution and atomic theory as one of science's great unifying theories, a framework that explains countless observations with elegant simplicity. The proof of a moving Earth. The evidence for plate tectonics and continental drift is now overwhelming. The magnetic stripes on the seafloor, the matching coastlines, the distribution of fossils, the continuation of mountain ranges across oceans, the patterns of earthquakes and volcanoes, the GPS measurements showing continents moving in real time, all point to the same conclusion. The Earth's surface is in motion. Continents drifting, ocean basins opening and closing, mountains rising where plates collide. We can observe it happening. GPS stations show North America and Europe separating at 2.5 centimeters per year. India pushes into Asia at 5 centimeters per year, raising the Himalayas higher. The Pacific Plate slides past North America, along the San Andreas Fault. The proof is irrefutable, measurable, undeniable. Pangea existed. It broke apart. The continents drifted to their current positions. They continue drifting. In millions of years, they'll assemble into new configurations. The Earth is dynamic, constantly reshaping itself. The proof of continental drift validated Wegener's vision decades after his death and transformed our understanding of how planets work. Earth isn't unique in having plate tectonics. Venus may have had it in the past, but among planets we've studied, it's unusual. Plate tectonics requires specific conditions: sufficient internal heat to drive convection, water to lubricate plate boundaries, and perhaps continents to help initiate subduction. Earth has all of these, making it a dynamic, geologically active world. The subduction zones beneath the seas. Subduction zones are where oceanic crust returns to the mantle, completing the cycle of plate tectonics. When an oceanic plate collides with a continental plate, the denser oceanic plate bends and descends beneath the continent. The descending slab pulls the rest of the plate behind it, one of the main driving forces of plate motion. As the slab descends, it heats up. Water trapped in the rocks is released, lowering the melting point of the surrounding mantle, creating magma that rises through the overlying plate. This magma feeds volcanic chains along the edge of the continent. The Andes, the Cascades, the volcanoes of Japan and Indonesia, all mark subduction zones. Subduction zones are also where the deepest earthquakes occur, generated by the descending slab as it bends, breaks, and grinds against surrounding rock. The deepest trenches in the ocean mark subduction zones. The Mariana Trench, over 11 kilometers deep, is where the Pacific Plate subducts beneath the Philippine Plate. Subduction is essential to plate tectonics. Without it, seafloor spreading would eventually cover the entire planet with oceanic crust. Subduction recycles old crust, maintaining a balance. The oldest oceanic crust is only about 200 million years old because anything older has been subducted. Continental crust, being less dense, resists subduction and can persist for billions of years, carrying the record of Earth's ancient past. The creation of mountains at the boundaries. Mountains form at plate boundaries through various processes. When two continental plates collide, neither can subduct. Both are too buoyant. Instead, they crumple together, the crust thickening and pushing upward. The Himalayas are the prime example. Formed by India's collision with Asia, a process that began 50 million years ago and continues today. The mountains rise about 5 millimeters per year, though erosion removes material almost as fast as tectonics adds it. When an oceanic plate subducts beneath a continental plate, volcanic mountains form along the continental edge. The Andes are the result of this process. When two oceanic plates collide and one subducts beneath the other, volcanic island arcs form. Japan, the Philippines, the Aleutian Islands. Rifting can also create mountains. As continents pull apart, the edges uplift, creating highlands that can be dramatic, even though they're being torn apart rather than compressed together. The mountains created at plate boundaries are temporary features in geological terms. They rise through tectonic forces, but are immediately attacked by erosion. Wind, rain, glaciers, and gravity wear them down. Eventually, all mountains are reduced to plains. The Appalachians, formed during Pangea's assembly, were once as tall as the Himalayas, but have been worn to gentle peaks. Mountains mark moments of tectonic activity, frozen in time until erosion reclaims them. The Himalayas and their ancient roots. The Himalayas are Earth's tallest mountains, crowned by Mount Everest at 8,849 meters. They're young by geological standards, having formed over the last 50 million years and still rising. But their story begins much earlier, with the breakup of Gondwana. India separated from Antarctica and Australia about 140 million years ago and began moving north, crossing the Tethys Ocean. Its speed was remarkable, perhaps 15 centimeters per year at peak, driven by the sinking of the Tethys seafloor, pulling it north. When India collided with Asia, the Tethys Ocean closed. The collision wasn't a sudden impact, but a slow-motion crash over millions of years. The oceanic crust, separating the continents, subducted, then the continental margins collided. India's northern edge crumpled, thickening dramatically. The crust in the Himalayas is twice the normal thickness, pushed up and down by the collision. The collision continues today. India pushes north at about 5 centimeters per year, though much of the motion is now accommodated by faults north of the Himalayas. The mountains rise, but erosion keeps pace. Rivers carving through rock uplifted kilometers above sea level. Marine fossils appear at Everest's summit. Limestone, formed on an ancient seafloor, now at the top of the world, testament to the power of plate tectonics to reshape the planet. The legacy of Pangea in today's world. Pangea's legacy surrounds us. The distribution of continents, the positions of oceans, the locations of mountain ranges, all reflect the supercontinent's assembly and breakup. The Atlantic Ocean exists because Pangea rifted. The Appalachian Mountains in North America and the mountains of Scotland are fragments of the same ancient range, torn apart when the Atlantic opened. The fossils we find, the rock formations we study, the mineral deposits we mine, many date from Pangea's time. Coal deposits formed from forests that grew in Pangea's coastal swamps. Oil and gas reserves originated from organic material buried in Pangea's seas. The distribution of life on Earth reflects Pangea's history. The unique faunas of Australia and South America result from isolation following Gondwana's breakup. The biogeographic patterns that puzzled early naturalists make sense when we understand Pangea's existence and fragmentation. Even our climate bears Pangea's legacy. The supercontinent's assembly and breakup altered ocean circulation, affecting global temperatures and rainfall patterns. The extreme climates of Pangea's time, the deserts, the megamonsoons, have no modern equivalents precisely because the continental configuration is so different. Studying Pangea helps us understand how Earth works, how continents move, how climate responds to geography, how life adapts to changing conditions. Pangea isn't just ancient history, it's the foundation of the modern world.